Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We are from group 9. We will present the assignment of spectroscopy. This is our group member Rafiki Akli, Alif Ilmi and Haris Hakimi. So our chosen allergen is propylene glycol. The IUPAC name is propane 12-diol. The chemical formula is C3H8O2 and the molecular weight is 76 gram per mole. The propylene glycol is a common ingredient in cosmetic, skincare product and personal care items. We will start with the first spectroscopy, which is IR spectroscopy. As we can see on the graph, there is a number of peaks that we can observe, which is 3350, 2970, 1377, 1138, 1045 and 839. So this FTIR spectrum of propylene glycol reveals key functional group through distinct absorption bands. The broad strong intensity peak at 3350 correspond to OH stretching, indicate of the hydroxyl group with hydrogen bonding broadening at the peak. The medium intensity peak at 2970 represent CH stretching from methylene and methyl groups, while the weak intensity peak at 1377 correspond to CH bending. Notably, the medium intensity peak at 1138 and the strong intensity peak at 1045 are characteristic of CO stretching vibration of secondary and primary alcohols, respectively. A weak peak at 839 correspond to the CH out of plane bending, while CH vibration are common in most organic compounds and often not emphasized in routine IR analysis. They are present here support the molecule's alkane structure. Overall, these spectral features confirm the presence of both primary and secondary alcohol group in propylene glycol.
Now, let's break down the interpretation of the 1H-NMR and 13C-NMR spectra for propylene glycol in simplest terms step by step. First, we need to understand what's the difference between 1H-NMR and 13C-NMR. For 1H-NMR, this spectrum helps us understand how hydrogen atoms, which is protons, are arranged in a molecule. Each peak represents a group of hydrogen atoms in a unique environment. Meanwhile, for 13C-NMR, this spectrum helps us understand the environment of carbon atoms in a molecule. Each peak represents a carbon atom in a unique environment. Here are the tables of 1H-NMR spectrum and 13C-NMR spectrum. So let's begin with the table for 1H-NMR spectrum. But before we dive into the interpretation of the tables, we need to discuss about the key information for each column in this table. For chemical shift, it tells us about the electronic environment around the hydrogen atoms. Meanwhile, ratio tells us the relative number of hydrogen atoms that produce each peak. And multiplicity, it tells us how many neighboring hydrogen atoms there are. Okay, now let's go to the interpreting the peaks. For 3.5 ppm, the ratio is 1 hydrogen. The multiplicity is doublet, which means it splits into 2 peaks because of 1 neighboring hydrogen. Assignment, this is the hydrogen atom attached to the carbon that is also bonded to a hydroxy group OH. When a hydrogen is near an electrowisdom group like OH, it shifts downfield, which is higher ppm. 3.3 ppm, the ratio is 2 hydrogens. The multiplicity is singlet, which means no neighboring hydrogen. Assignment, these are the hydrogen atoms in the hydroxy groups OH. OH groups have broad singlets because they exchange hydrogen with the environment, which affects the splitting. 1.1 ppm, the ratio is 3 hydrogens. Multiplicity triplet, which means it splits into 3 peaks because of 2 neighboring hydrogens. Assignment, these are the hydrogen atoms in the methyl group CH3. Methyl groups appear upfield, lower ppm, and are split by adjacent CH2 hydrogens. Okay, now let's go into the 13C NMR spectrum table. Okay, let's interpret for each peak. We start from 68.2 ppm. The ratio is 1 carbon. Assignment: this is the carbon bonded to 2 hydroxy group CH. Carbon bonded to electron withdrawing groups like OH appear downfield, which mean higher ppm. And 67.8 ppm. The ratio is 1 carbon. Assignment: this is the secondary carbon CH2 adjacent to the hydroxy group. The carbon is also influenced by the OH group, hence it appears downfield. Last is 18.6 ppm. The ratio is 1 carbon. Assignment: this is the methyl carbon CH3. Methyl groups appear upfield, which means lower ppm because they are less affected by electron withdrawing groups.
Now we move to the next spectroscopy, which is mass spectroscopy for propylene glycol. So these are the mass spectra for propylene glycol, and from the spectra we also can know the molecular ion, which is 76 Dalton, and the base peak, which is 45. And then we move to the next part, which is 3 possible fragmentations and the chemical reactions involved for each fragmentation. So there are 3 fragmentations from this mass spectroscopy of propylene glycol. First, fragmentation 1, which is formation of CH2OH plus with the 31. These fragmentations involve the cleavage of the bond between the central carbon, which is C2, and the terminal hydroxyl group, C3 with OH, resulting in the loss of a methanol molecule, which is CH3OH, and the reaction is CH, CH, CH. It will produce CHOH plus CH2OH. And then for the fragmentation 2, which is the formation of CH3, CHOH plus for mass to charge ratio, which is 45. These fragmentations involve the cleavage of the bond between the central carbon, which is C2, and the other hydroxyl group, C1 with OH, resulting in the loss of water molecules, which is H2O, forming the CH3CH OH plus ion. And the reaction is CH, CHOH, CH2OH, and it will produce CH, CHOH plus H2O. And for the next fragmentation, which is fragmentation 3, the formation of CH3, CH plus for 29 MZ. These fragmentations involve the cleavage of the bond between the terminal carbon C1 and the central carbon C2, resulting in the formation of the CH3 CH plus ion in the loss of the hydroxymethyl radical, which is CH2OH, and the reaction is CH3 CHOH CH2OH. It will produce CH3 CH plus CH2OH. So that's all for the mass spectroscopy, and that's all from us. Thank you and Assalamualaikum.